So on this page, we're going to look at a couple examples that seem like they're in rectangular, but they're not going to stay that way. All right, so for this particular one, example 2, we're asked to evaluate this integral. So we're looking at the integral and it's got dy dx in it. Right, but look at these coordinates. Ugh, right? Just ugh. Right? The integration in rectangular is terrible. Right? We don't like dealing with ugly integrands like that, and that one's not great either. Big frowny face, right? But y equals the square root of 1 minus x squared, we know what that is. Think about that. What is y equals the square root of 1 minus x squared? That's the top half of a circle. So y is going from 0, right here, y equals 0, to y equals the square root of 1 minus x squared. And then x is going from negative 1 to 1. Right. So this is going to be way easier in polar. That's a general trick for you. If it's a circle, polar is usually easier. Okay, so we're going to switch this to polar. So switch to polar because R is a circle, right? Your region of integration is a circle. Most of the time when your region of integration is a circle, it is easier in polar coordinates. Okay, so we're going to rewrite this. E to the, okay, wait. X squared plus y squared, remember, x squared plus y squared equals r squared. So that's e to the r squared over 2. And then instead of dy dx, we write r dr d theta, right? So dy dx turns into this, right? And then this is the x squared plus y squared. Okay, so then what about our limits of integration? Okay, so we have to think about a spoke coming out of the pole in our polar coordinates. So r would go from 0 right here to 1 right here. So r goes from 0 to 1. Theta starts over here at theta equals 0 and goes all the way around to theta equals pi. So we're going to go 0 to pi here for d theta. Now, these are all numbers. So for all intents and purposes, we can put them in whatever order we like. Now let's look at this integrand for a second. It's r times this thing, right? That's the integrand, right? Matter of fact, I can put parentheses around it, right? It's there. There's no theta in it. So this is a trick that we use sometimes, beginnings of a trick. So there's no theta in the integrand. So rearrange the order. Rearrange, right? D theta first. Okay, so let me rearrange it. So instead of going 0 to pi, I'm going to go 0 to 1. And then I'm going to go 0 to pi. And then I'm going to say r times e to the r squared over 2. And then I'm going to say d theta dr. Why did I do that? Well, because the integral of this with respect to theta is the whole thing times theta. So, I mean, it doesn't get much easier than that. So this is r times e to the r squared over 2 times theta, where theta goes from 0 to pi dr. Okay, but that's just pi times this whole thing, because pi take away 0, right? So this whole thing becomes 0 to 1 pi r e to the r squared over 2 dr, and we're going to make Maple do that. All right, so let's go look at Maple. Okay, so just so you can see, there's the surface right there. There's the shadow that's cast. It's definitely a semicircle. I did the original integral as it was given, and then I got a decimal approximation. And then I did the integral as we changed it. And this is a way you can check that your changing of things was correct, right? You can verify that the original given integral and your new polar integral are the same. And sure enough, they both become 2.0380. And then I did it after I had done the integration as well to make sure that I integrated correctly with respect to theta, which I did, and it gets me 2.0380. So I just went and put those values in. I put in the exact one, which I've forgotten this had given as an exact one, and then the approximation. All right, let's look at the next example. Wants to find the volume above the xy plane and below this surface. 20 over 1 plus x squared plus y squared minus 2. Let's go look at that in Maple real quick to see what this looks like. Okay, here's what it looks like. It's sort of like a wizard's hat, right? But you can see that the shadow that it casts is actually a circle. And by the way, you can tell how ugly the limits of integration are so that I'm having to do this. So that's a kind of a sign that this is going to be definitely better in polar. So let me draw that picture, that wizard's hat kind of picture. All right, so let's see here. We've got z-axis, y-axis, x-axis, and then we're going to kind of draw a kind of sloping hat kind of a thing. And then it connects up in a circle down below. So that region of integration, oh, actually, let me put it this way. That's what we're really interested in. And I like drawing in a maple because then you can kind of tilt it around and see that it's a circle. So the region of integration is a circle. This is the y-axis, this is the x-axis. There's our r. Okay. So, and we're going to have to think about a spoke coming out of that region. We'll deal with that a little bit later. Okay, so let's go look at our double integral. So when we want to find the volume is the double integral of the function dA. All right, but we don't have to work with dA in terms of x and y if we don't want to. But we'd have to change our function, which is currently written in x and y form, so we can't leave it like that. But remember that x squared and y squared makes r squared, right? So this is 20 over 1 plus r squared minus 2 times dA would be r dr d theta. Okay, so then r. So let's look down here. This is the part we really have to think about. Actually, let's do theta first because theta is easy. Theta is no problem. And actually, I'm going to do these in different colors just like I did on the previous one. So d theta I'll do in blue, dr I'll do in pink. Okay, so theta is really easy because theta starts over here and then it goes all the way around and ends up in the same spot. So theta is 0 and 2 pi. Easy, right? Both constants, no problem. R is the one that's going to take a little bit of work because where is this radius happening? Where are we hitting? What's going on here, right? We need to know where this is. Okay, so to do that, we have to think that was where this surface, this wizard's hat, was hitting the xy plane. So the z, which was 20 over 1 plus r squared minus 2, was equal to 0 because the xy plane has z equal to 0. So that means I'd add 2, so 20 over 1 plus r squared equals 2. So 20 equals 2 times 1 plus r squared. So 10 equals 1 plus r squared. So r squared, whoop, I'm going to have to put it over here, r squared equals 9. So r equals plus or minus 3. Which of course the negative doesn't do us any good, so we're not really worrying about negative r's. Negative r's just make it go into the back instead of the front. So from the thing. So r equals 3. So r equals 3. And of course it's starting at the origin and going the whole way out. This whole thing is filled in, so it's 0 to 3. So 0 to 3. Okay, well, now you're thinking, oh my goodness, this is going to be a really hard integral to do. Well, it would be if we did r first, but we're not going to do r first. we're going to do theta first. So let's rewrite this, and I'm actually going to teach you a little trick. So when you look at this integrand, you notice there's no theta in it. Actually, let's back up. This previous one, when there was no theta in it, did you notice what happened? Right? We integrated, we got theta, and then it just became the difference in pi take away 0. And so it just became this pi sitting right here, which we knew it was going to be pi in the first place. So why bother showing the work? Ah. And we're going to use this trick all the time, right? So we're going to say, look, there's no theta in this integrand. And so we're going to get rid of the theta. So if you integrated with respect to theta first, right? If you did that, it'd just become theta from 0 to 2 pi, and then it just become 2 pi, right? Because the difference in 2 pi minus 0. So let me show you the work, but I'm not going to do it anymore after this. So this is 0 to 3, and then it becomes this whole giant thing, 20 over 1 plus r squared minus 2 times r. And then theta goes from 0 to 2 pi dr. And so then you just go, well, that's silly, right? That's just 2 pi, right? 2 pi take away 0 is 2 pi. So it just becomes 2 pi out in front of the whole thing. Actually, let me do it in blue because that's where it's coming from. It's coming from that theta. So it's 2 pi take away 0, which is 2 pi, times the integral from 0 to 3 of this whole mess. R times 20 over 1 plus r squared minus 2 dr. And so what happens is we generally skip this step and go right from here to here. And we skip this over because we see that there's no theta in the integrand. And so we can skip from this down to here. And when we do that, what we do is we cross these off and just write a 2 pi out in front, just like I did here. And then I make Maple do the last step, right? That's what Maple is for. Oops, let me that was work on the side. I don't want to get it confused. All right, so let's go look at the Maple. But that particular trick we are going to use all over the place. When there's no variable value in the integrand, you can basically just take the difference in the integral limits and just stick it out in front because it'll be some constant. And it's about 88.128. And you can see here, I'm proving that it works. So there's the original integral with theta going from 0 to 2 pi. Here's the, hey, shove 2 pi out in front and still do the integral. And sure enough, both times we get 88.128. Now, it didn't give us units. So let's pretend x, y are in inches. If x and y are in inches and we're finding volume, then this would be inches cubed.